In this lesson, we're going to discuss direct and inverse variations. So a direct variation, verbally you'll hear it spoken as it's something that varies directly, is there's a specific equation for it, and it looks like this. Y equals some constant, that's what that is, some constant times x. And if x goes up, then y is going to go up. That's the idea of varying directly. So as one thing goes up, another thing is going to go up. Exact opposite is true. If x goes down, then y is going to go down. All right. So visually, we're talking about a graph that looks something like this. Very much a linear equation, and it has a y-intercept of 0. And as x increases, so if x goes from here, here's the y value. If it increases, it causes the y value to increase. All right, same thing is true if you have this x value and it goes down, your y value goes down as well. So kind of an example of that would be if you get paid hourly. So the more you work, then more money. So as your hours increase, your salary increases. As your hours decrease, your salary decreases. So that's the idea of a direct variation. An inverse variation is the opposite of that. So equation-wise, it looks very different. Equation-wise, we're going to take some sort of a constant again, and we're going to divide it by x. So this time, if x goes up, the idea of an inverse variation is that then y is going to go down. So if x decreases, then y increases. All right, so graphically, it becomes a rational equation, and it looks something along those kinds of lines. So if x goes from this value and it increases, it makes the y value decrease. So as x decreases, the y value increases. So an example of that would be if you have more people working on a job, so if more people are working on a job, then in theory, it should take less time to complete. All right, and there's all sorts of different examples, but those are just kind of some really quick ones that most people can kind of relate to. So, direct variation, this is the particular equation that we're going to be using. All right, that's kind of the equation that I'm thinking of anytime I hear a direct variation, and if I hear an inverse variation, this is the equation that I'm going to be thinking about. So, we have an example. It says transportation costs. So we have to take something out of a word problem, we got to create an equation for it, and then see if we can solve it. So first thing is, let's figure out which situation we have going on. For the transportation cost, says the use of a toll bridge varies inversely according to the toll. So when the toll is 75 cents, 6,000 vehicles use the bridge. Estimate the number of users if the toll is 40 cents. So it does say inversely. All right, so instantly I'm thinking of this kind of equation. All right, but I'm going to write it more in the terms that they give me. So it says that the toll bridge, the use of the toll bridge, we are talking about so many vehicles crossing. So the vehicles vary inversely. So there's always some sort of a constant, always, and they vary inversely. So again, this is the equation, but this is our vehicles are varying inversely according to the toll. All right, so X is going to be represented by our toll, our Y is going to be represented by our vehicles. So now we have our situation, but we don't know our constant. We have a situation that gives us both the vehicles and the toll, this right here. So at 75 cents, we have some constant divided by 0.75. We get 6,000 vehicles to cross the bridge. All right, so if we can solve for k, that'll give us our constant, and then we can use it for any situation that they ask us. So to clear out the fraction, we're going to multiply both sides by 0.75. All right, so if we do that, values on the left or on the right are going to cancel, and we're going to have our constant is going to equal 4,500. All right, so now we can go back to our original equation, and now we have a value for our k. So now they can talk about any situation. They give us vehicles, we can find the toll, they can give us the toll, and we can find the vehicles. So it just depends on what the question is that they're looking for. So the question is, estimate the number of users if the toll is 40 cents. So we don't know the users, the vehicles crossing the bridge, so that's still our variable. We have our constant, and then we're going to divide by 40 cents. So if we type it in the calculator, do the math, that gets us 11,250 vehicles. All right, so that's our first example. All right, our second example is talking about a braking distance. It says the distance d required for a car to stop when braking varies directly, so I'm going to underline that, varies directly to the square of the car's speed x. If a car moving at 60 miles per hour requires 300 feet to stop, how many feet would be required to stop the car at 30 miles per hour? So the fact that it's a varies directly, I'm thinking of this kind of equation. All right, but again, I got to relate it to the variables and everything that they're talking about here. So it does say that the distance d, so that would be our y value, the distance d varies directly to the square of the car's speed. So it's still going to be some constant times x. The speed is x, but it's the square of the speed. So that makes it look like that. Still a varying directly, it's just messing with the equation just a little bit. So they give us the situation, see if we can find out what k is, and then again we can answer any question that relates to it. So if a car is moving at 60 miles per hour, so that is not our distance, that's going to be our speed. So we have k times 60 miles per hour squared requires 300 feet to stop. That is our distance. All right, so we will try and solve for k. So 60 squared is 3,600. K equals 300. We'll divide by 3,600. And I'm going to reduce this fraction. Those two zeros will cancel those two zeros. The 3 goes into 36. 1 time for the 3, 12 times for the 36. So our k value is 1/12. So jump back to the original. The original was d equaled k. We have a value for that. And then times x squared. And x is our speed. So we use the 60 and the 300. It says how many feet is it going to require now to stop the car at 30 miles per hour? So we don't know the distance. They're asking that of how many feet. So it's going to be 1/12 times our speed, which is 30 squared. So that distance is going to be 1/12 times 900, and 1/12 times 900, that distance ends up being 75 feet. So again, with both these equations, we want to make sure that the answers make sense, and we'll go back to the other one in a second, that since it's varying directly, and we had an original problem that had 60 miles per hour, took 300 feet. If it's varying directly, we are lowering our speed, so we should be lowering our distance. They go together like that. That's the idea of a direct. So lowering our speed is lowering our distance, which that matches. So that's a good indication that we use the right equation, that we set it up. I go back to the first one. First one was inversely related. So this time, if our money is going down, our vehicles should be going up, which is exactly what we have going on. 75 cents goes to 40 cents, so that's going down. Our vehicles are going from 6,000 to over 11,000, so that's going up. So that also, that idea matches. All right, and that was direct and inverse variations.